Hello everyone, and today's lecture is going to be on simple harmonic motion, our next lab. Okay, when we think about simple harmonic motion or simple harmonic oscillators, we think about things that go back and forth. And when things go back and forth, there is always a restoring force involved. And a restoring force here for what we're going to be doing is using springs. And when we talk about springs, we have to talk about Hooke's law. Hooke's law applies to any material that returns to its normal shape whenever the force stops acting on it. So of course, if you have a spring, you pull on it, you let go, it goes back to its original shape. Hooke's law involves a stretching force or a compression force that is proportional to the amount, a stretching force from a body or a spring that is proportional to the amount of force applied to it. And that proportionality is what we call K, which is the spring constant. Here we have Hooke's law in equation form. So it's F equals negative Kx. So F is the restoring force of the spring, always points towards the equilibrium point. X is the distance or the displacement from equilibrium. K is the spring constant, which we'll talk about a little more on the next slide. And the negative sign tells you that the force is acting opposite to the direction of displacement. And here we're going to talk about the spring constant, which is K. K is given to you in units of newtons per meter. So it tells you how much force you will need to stretch a spring a distance of X. It also tells you how stiff the spring is. And if you notice from the picture that you have the stretch from equilibrium, you have the external force causing the stretch, and that your slope equals K, the spring constant. Hey, in our lab, you will be measuring the spring stretch as hanging masses increase. With that data, you will determine the spring constant of these springs. You'll also be using a force probe, and so we'll have some springs on the cart, and we'll get to do all kinds of neat little things. So be prepared to do some measurements. Now we can start talking about simple harmonic motion. Simple harmonic motion or oscillation is back and forth motion caused by a force that is directly proportional and opposite in direction to the displacement. And the displacement centers around an equilibrium. So here we have a mass sliding along a frictionless surface attached to a spring. And in one direction, the spring is compressed and it pushes away. In the other direction, the spring is extended and it pushes back towards the spring. So it will move back and forth forever, and it will oscillate around that initial points of equilibrium there. You can also take a look at a pendulum. A pendulum will also swing back and forth, but its restoring force is gravity. Simple harmonic motion is also periodic, which means that you can model it with sines and cosines. So here we have displacement versus time. We have velocity versus time and acceleration versus time. As you notice, they all look like sine and cosine waves. However, there are some important things to notice to think about as to when is displacement maximum, when is velocity maximum, when is it zero, when is acceleration maximum, and when is it zero. And those relationships are what we're looking for in our next lab. To finish things off, there are a couple of more equations that you'll need to be familiar with. One is the period. This tells you how long it takes to go one full oscillation, or to go 2 pi. For a spring, the spring constant K and mass M, its oscillation is T, being the period, equals 2 pi times square root of M over K, mass over the spring constant. And then for a pendulum, it's T equals 2 pi L over G. Notice in the pendulum that there is no mass, it's only the length and gravity. So the only thing that's variable is the length of the pendulum. All right, well, that is everything. So we'll see you guys in class. Talk to you later. Bye-bye.